Welcome to this tutorial on how to set up a new conveyor using Belt Analyst. This example will go through the basic process for setting up each of your design parameters. We will be starting with one of the preloaded templates in Belt Analyst for a horizontal conveyor. You do have the option of saving your own conveyor template with values commonly used by your company. For our example, click the New button. Select Horizontal Conveyor, Head Drive, Head Take-Up in English units. Save the conveyor in the desired project folder. If you are prompted to save your project file in a new file format, click Yes. This is due to Belt Analyst having pre-existing versions. If you want to save the file so that it can be used in older versions, click No. If you look at the right-hand side of the screen, you will see the basic setup of your conveyor. You have the cross-sectional area of the carry and return idlers. You have the current profile, shown here as fully loaded, which is the default. You also have the basic information like width, speed, load, and the ambient temperature. And at the bottom of the right side is the overview of the tension seen by the conveyor. On the left side, you will see tabs that represent the important components of the conveyor. The first tab is the Notes tab, where you can name your project and insert any special notes about the design. The second tab is the Materials tab, where you can choose the material that would be carried on the conveyor. The Flights tab is where you can define the geometry of the overall profile. The Belt tab is where you can choose the belt specifications. The Idler tab is where you can specify the number of idlers, the geometry of the frame, and the grade of the idlers. The Drives tab is where you can choose the size of your motor. The Take-Up tab is where you define the weight or the tension of the take-up. The Pulleys tab is where you can choose the size, lagging, and other specifications of each of your pulleys. The Vertical Curves tab is where you can input the radius of a concave or convex curve. None is shown here at the moment because there are no vertical curves on our conveyor. The last tab is the Trajectory tab, which shows the trajectory of the material off the end of the belt. This is mostly used for chute design. We typically like to start with the information on the right side of the screen, then move through the tabs from top to bottom as we design the conveyor. When you begin your conveyor design, you need to ask yourself what kind of conveyor you are looking at. Is it a pre-existing conveyor, where you know the information on the right side of the screen and want to find the components that will fit those specs? Or are you trying to model them to fit a specific need you may have? In this case, we will use the pre-existing conveyor with the head drive and the head take-up on a horizontal conveyor where the specs are already known. We will set the width of the conveyor to a 36-inch belt. We will choose a speed of 450 feet per second. And we will set the load to be 800 tons per hour. We will also set the ambient temperature to 32 degrees Fahrenheit. After you enter each value, you can see the program has recalculated based on the new values. So now we will go through each tab starting at the top. So if we click on the Materials tab, you can see that there is a material description box at the top of the table. It has a drop-down option. This list contains material that we think are the most commonly used in conveyor design. If you find that the material you want is not available, you can always click the first combo box and type in the material description manually. So for this example, we are going to use gravel bank rag. When we select it, Belt Analyst will update the material density to 100 and the surcharge angle to 19. These values along with a given load of 800 tons per hour, will define the cross-sectional area of the material on the idlers, as shown on the right. Now that we have selected our material, we will move to the geometry of the conveyor. When we click on the Flights tab, you will see the default flights from the template that we loaded earlier, which was a horizontal conveyor with a head drive and a head take-up. Here is where you would input your existing geometry of your conveyor. For our example, we will say that there is 200 feet of flat conveyor followed by 400 feet of conveyor at a 6-degree vertical lift, then 200 more feet of flat conveyor. So to do this, click the first box under the horizontal length and enter 200. You can then either enter 0 for the lift or for the angle. One will be calculated off of the other. In the next flight, we will enter 200 with an angle of 6 degrees. We will do the same for the next flight. And lastly, we will enter in 200 and 0 for the angle. If you need more or fewer, so if we click on the Materials tab, you can see that there is a material description box at the top of the table. It has a drop-down option. This list contains material that we think are the most commonly used in conveyor design. If you find that the material you want is not available, you can always click the first combo box and type in the material description manually. So for this example, we are going to use gravel bank run. When we select it, Belt Analyst will update the material density to 100 and the surcharge angle to 19. These values, along with a given load of 800 tons per hour, will define the cross-sectional area of the material on the idlers, as shown on the right. Now that we have selected our material, we will move to the geometry of the conveyor. When we click on the Flights tab, you will see the default flights from the template that we loaded earlier, which was a horizontal conveyor with a head drive and a head take-up. Here is where you would input your existing geometry of your conveyor. For our example, we will say that there is 200 feet of flat conveyor followed by 400 feet of conveyor at a 6-degree vertical lift, then 200 more feet of flat conveyor. So to do this, click the first box under the horizontal length and enter 200. You can then either enter 0 for the lift or for the angle. One will be calculated off of the other. In the next flight, we will enter 200 with an angle of 6 degrees. We will do the same for the next flight. And lastly, we will enter in 200 and 0 for the angle. If you need more or fewer flights than what was given in the template, you can click a location and click either Insert Flight or Delete, respectively. Say that you need a 5th carry flight. You would click the first column next to the section 5, then click Insert Flight. To delete, you would click the flight you want removed and click Delete. You will notice that for every carry flight, there is a matching return flight. This will be the case when the Flights tab is in Standard mode and Auto Return mode. If you look at the drawing, you will see that the take-up pulley, or the blue pulley, is at the head. For this example, we are going to put the take-up pulley at the tail. To do this, click the take-up pulley and click Move. Click the location you want to move the pulley to, which in our case is the tail pulley. Once I move the take-up pulley, the tail and take-up will combine and location 12 should read tail/TU. Typically, you will not have two bend pulleys next to each other without a segment of belt in between them. In our example, we only need one bend pulley after the head, so we can go ahead and delete one of them. When you click delete, Belt Analyst will ask if you are sure you want to delete the pulley. Click yes. So we have our head pulley, which is our drive pulley, and our bend pulley, which in this case will act as a snub pulley. We can add labels to the pulleys by clicking in the label column next to the pulley and typing SNUV. A couple things to look at while on the Flights tab are the idler spacing and the percent load. The default in this case has the idler spacing set to 4 feet for the carry side and 12 feet for the return flights. I can change each flight's idler spacing individually. For example, the first 200 feet might have a spacing of 5 feet, while the others have 4 feet. Or I can change all of them at once, as shown in the previous videos. For our example, we will set the idler spacing to 5 feet for all carry flights and 10 feet for all return flights. In the percent loaded column, you have 100% load for each of the carry flights. If there is a section of conveyor that is not going to have material on it, you can enter 0 for the percent loaded. This will show that the material starts on the incline up until the end. Another thing to notice is that the Flights tab has a scroll bar at the bottom. You can use this to scroll to the end of the table, or you can click Expand Folder, or the hotkey F8. There are columns to add skirting, cleaners, or plows to each flight. There is also a column for extra drag. This is where you would add any extra weight or drag that is seen by the conveyor. For this case, we will say there is 15 feet of skirting at the beginning of the conveyor. We will add one cleaner at the head and 2 cleaners after the snub pulley. We also have one plow right before the tail. You can click the Contract Folder button to get back to the normal view. The geometry is now set up and we can move to the Belt tab. You will notice that the Belt tab is a cyan color and will turn gray once we change the database to user to lock in the values. So let's click on the user database and we can see all the options we have available. If we choose the fabric belt US and choose a 2-ply 220 PIW rating, we will notice that the Belt tab, as well as some of the text in the table, such as the max running tension and the max XL tension, are red. This indicates that there is an error with this choice of belt. So in our example, we will select a fabric US belt with a carcass of 3-ply 330, which was the default value that Belt Analyst chose for this situation. There are no red values, which indicates that all values are acceptable. We are now finished with our Belt tab and can move on to the Idler tab. As you can see, the Idlers tab also has the Auto database, User database, and Custom options at the top of the table. This works the same way as the Belt tab. In Auto, Belt Analyst is calculating the minimum required idler for this application. These values will change based on the changes made to the rest of the program. If the tab is in User mode, no values will change during the design process. So we are in User mode and can input our own data. We can click the down arrows in the specification and the descriptions for both carry and return sides. When you make a selection, the drawing will update as well as the calculated values in the program. And for this example, we will use the C4 idlers for both carry and return in this SEMA 5 database. You do have the option to change the angle of the trough to be 45 degrees, 35 degrees, or 20 degrees for the carry side. If you have two rollers for the return side, you can change the angle of the trough to be 5, 10, or 15 degrees. In our case, we are going to leave the idler trough at 35 degrees. If you had a specified roller for your conveyor, you would input that data here. You have completed the idler tab now, so let's move on to the drives tab. The drives tab also has the auto and user modes. For our example, we will be in user mode. If you take a look at the top of the table, you will notice the total nameplate power and the running power. In this particular example, the running power is at 82 horsepower, which is also 82% of the total power. The running power is calculated in Belt Analyst. Some other values to note are the efficiency, power ratio, and the brake ratio. The efficiency of the motor is determined by the manufacturer. The power ratio can be changed if the load is shared between two or more motors. The brake ratio can also be split between multiple pulleys. The wrap angle cell is another place to change the wrap angle of the head pulley. The slip ratios during running and acceleration will be determined by the wrap angle. We will input a wrap angle of 210 degrees for our head drive pulley and set our lagging type to plane. If you click the Summary Data tab at the top left corner of the window, you can view the overall breakdown of the forces seen by the conveyor. We have now completed the Drives tab, and we'll move on to the Take-Up. So the Take-Up tab is defaulted to Auto mode, which means that the take-up tension and the weight have already been selected for you based on 6 different values. These values include the minimum take-up tension required to prevent sag during running, acceleration, and drift, as well as the tension required to prevent slip during running, acceleration, and drift. It then finds the highest number of those 6 values and adds 10%, which gives you the 3,740 pounds of tension. If I flip the Take-Up tab to User, it allows me to edit the tension or the weight, and let's say in our example we have an even 4,000 pounds. So now that our take-up tension is set, let's take a look at the pulleys tab. In this example, we will only look at the basic design for the pulleys. When basic is selected, Belt Analyst will remove any calculations for shafts, deflection, and bearings. We can see the table showing the 3 pulleys that we have in our Flights tab. It shows the locations of each pulley, which is location 5, 6, and 11, as well as their T1 and T2 tensions. These values would be given to the manufacturer for their design process. If you are not in basic mode, you have many more design options, such as hub design, bearings, and shaft design. So now that our pulleys are finished, we will move on to vertical curves. You can see that the vertical curve tab is in auto. The auto mode selects a value that will prevent excessive liftoff if it's a concave curve, and looks at the high and low edge or center tensions for a convex curve. Belt Analyst will then select the highest value and then set that number as the radius of the curve. In our case, the radius to prevent liftoff in the first curve is 406 feet. This value represents the carry side of the conveyor. You will notice that matched up on the return side is flight 10. And you can see below that it says also 2, which is also flight 2. This flight will have its own set of radius calculations. If the radius for its corresponding carry flight is greater than its own highest radius, it will take the higher value. This is the case because we have automatic return sections, which means the carry and return concave curves match up. If the Flights tab was in User Return mode, where the carry and return flights don't necessarily match up, each flight radius would be separate. For the convex curve, Belt Analyst will look at the tensions of the belt at the edge and at the center. It will calculate to either overstress or understress the belt, what the radius would need to be, and then print out the value. If we expand this folder, we can see that Belt Analyst also outputs a load per idler tension, which includes excessive loads due to the curve radius. It then suggests the idler spacing to prevent those excessive loads. So for our example, we will click User, and we will input a 450-foot curve radius, and we will stay with an 80-foot radius for the convex curve. So let's contract this folder and move on to the last tab, which is the Trajectory tab. This tab shows you where the material will travel as it leaves the conveyor, which you can use in a chute design. So now we have finished the input process for this conveyor. In order to complete the design process, you would need to put the conveyor through different cases in order to test the capacity of the components you selected. For example, dropping the temperature that the conveyor runs in, or changing the load conditions, as would be seen on site. As you go through each of your cases, look for components that turn red, which indicates an issue. That concludes this tutorial for the basic design of conveyor. Thank you for watching, and if you have any questions, please contact Overland Conveyor.